All right, this is our review for our Unit 3 test. This is over Chapter 5 out of the textbook, sections 5.1 through 5.4. So I'm going to work through the review. It may take 2 videos to get all the answers in. I'm not really sure yet. So if we get towards the end of the review and I'm getting close to my 15-minute limit, then I'll have to stop it and we'll start a new video. So it'll just be part 1 and part 2. So starting with the first part, this is from section 5.1, and basically you're looking at these graphs to tell whether they are a function first, and then whether they're a linear function. So looking at example number 1, this is a function because it would pass the vertical line test if you were to perform the vertical line test, basically meaning that you draw vertical lines anywhere on the picture. It should only touch it one time. So as far as it being a function, it is a function, so we would put yes for that. And then linear, remember, means it's a straight line. And so obviously this is a straight line graph, so that would get a yes also. Yes, it is a function, and yes, it is linear. Now number 2 is also a function. If you performed the vertical line test on this one, you would see that the vertical line would never touch the graph in more than one spot at a time. So it is a function. Obviously, this one is not linear, so that would be a no, because it isn't a straight line. Okay, number 3. 3 and 4, you're going to look at these and be able to tell whether the table or the set of ordered pairs is a linear function. And so what I like to do, if I have a set of ordered pairs, I create a table out of it, similar to number 4. It's just easier for me to tell if we've got a linear situation here. What you're looking for when you look at a table is to see if there is a consistent rate of change in your x values and in your y values. And if it does have a consistent rate of change, then it would be a linear function. So I'm going to fill in my table first. I've got -2 and 5, -1 and 3, 0 and 1, 1 and -1, and then 2 and -3. So I'm going to look at my x's first and see what kind of change is occurring. From 5 to 3, it went down 2. From 3 to 1, it's going down 2. And each time this is progressing down, it's going down 2 every single time. So that has a consistent rate of change with the y's. Now looking at the x's, each time this is progressing up, it's going up 1 every single time. So for number 3, that would be a yes. It is a linear function, and the reason why is because you have a consistent rate of change for your x's and y's. So we'll do the same exact thing for the table on number 4, and I'm going to notice that for every single one of these changes in y, it's going up a quarter, or 0.25 each time, and it's consistent all the way through. I'm also noticing on my x's that every single time it's stepping up, it's going up 4 units every single time. From -10 to -6 it goes up 4, -6 to -2 it goes up 4, and likewise. So because that has a consistent rate of change, it is also a linear function. Looking at 5 and 6, when we tell if an equation is a linear function, there's things that we're looking for that might be occurring in the problem that would tell us if it's not linear. So if we don't notice any of those patterns in the problem, then we're looking at a linear function. The things that we looked for before, and we wrote these in our notes, but just as a reminder, it's kind of all the effects that the equation might have on the x. For example, if the x is squared or to any other power, then it's not linear. These are examples of things that would make an equation not linear. So if it had an x squared, perhaps if it had an absolute value of x, if it had a square root of x, if the x and the y were multiplied times each other, if the x was an exponent, for example, if I had 2 to the x power, or if there was a fraction and the x was on the bottom. All of those are examples of things that are not linear, and pretty much everything else is. So if we look at number 5, that one definitely is a linear function, and you could even type that graph in. Type that in on the y equals screen, -3x plus 2, and look at it and see that it is linear. Likewise, this one, if you typed it in on the y equals screen, 2x to the third power, you would see that it's definitely not linear. It doesn't make a straight line, but also we talked about the fact that effects on the x, like if there's an exponent on the x, it's not linear anyway. So you do have a backup plan if you need to use your calculator to look at it to tell whether it's linear or not, if you don't remember these specific examples of things that are not linear. All right, number 7 and 8. 7 and 8, we're looking to see if we're looking to find our x and y intercepts, and then from those x and y intercepts, we're going to graph. So on number 7, my equation would be 3x minus y, and I'm going to put 1y equals 6. I like letters to be in front, or numbers to be in front of the letters. It helps in the solving process. So when you're finding the intercepts, basically you're looking for the x-intercept, which has a 0 right here. The y-intercept has a 0 right there. So I write those ordered pairs down like that to begin with, and then once I fill in and I do the work, I can go back and fill in my answer. So if I'm looking right here for the x-intercept, I'm going to plug in a 0 for y right there. So I would have 3x minus 1 times 0 equals 6. Well, basically, negative 1 times 0 is 0, so that cancels out. And I get 3x equals 6, which would mean x equals 2 after I divided. So my x-intercept is 2, 0. Do the same exact process again, but this time let's do it for the y. We've got 3x minus 1y equals 6. This time I'm going to put the 0 in for the x. So if I put a 0 in right there, 3 times 0 would be 0. It cancels away. And I'm left with negative 1y equals 6. If I divide both sides by negative 1, I get y equals negative 6. And that is my y-intercept. So if I plot those 2 points, 2, 0 is here, 0, negative 6, I believe is right there, and then connect them together to make your graph. Same thing on number 8. I've got negative x plus 2y equals 4. I'm going to create an x-intercept, and I'm going to create a y-intercept. All right, let's do the x-intercept first. For the x-intercept, you plug in your 0 for the y. So if I put in a 0 right there, that makes this cancel away. I get negative x, I'm going to make it negative 1x, equals 4. Dividing both sides by negative 1, therefore x equals negative 4. That's my intercept. Then if I do, that's my x-intercept. If I do the other one, negative x plus 2y equals 4. This time I'm going to put my x in, or my negative 1 in, with my 0 in for the x. So my 0 would go right here, making that value cancel. You get 2y equals 4, therefore y equals 2. X and y intercepts. So I'm going to put a dot on negative 4, 0, dot on 0, 2, and then connect them together to make my graph. So on number 9, you're looking for the intercepts, and they're right there. That one is your y-intercept because that's where the graph crosses the y-axis. That would be 0 and 4. This one is your x-intercept because that's where the graph crosses the x-axis. That one would be negative 2, 0. All right, moving on. Number 10. Number 10 was a challenge today in class because it's a word problem. Well, that's hooey. It's not hard. It's exactly like the problems that we just did. So when you find the x and y intercepts for this problem, that's going to give you the answers that you'll graph, and then you need to describe what the intercepts mean. So basically for this one, we're going to take the equation f of x equals 50 minus 10x. Now, we can write y equals if we want to. Instead of putting f of x, you can put y equals 50 minus 10x, and then from that, we're going to do the intercepts. Exactly same process we did just a minute ago. We're going to find our x-intercept by putting in a 0 for the y. We're going to find our y-intercept by putting in a 0 for the x. So first of all, I'll do the x-intercept. I'm going to put in a 0 for y over here. So I get 0 equals 50 minus 10x. Well, to solve this, you can do it in a variety of ways. Most of the students I saw today were doing this. Moving the 10x over. So you get 10x equals 50. And then if I divide by 10, x equals 5. So your x-intercept is going to be 5, 0. Okay, let's do this process again, but this time let's put in our 0 for the x. If you get y equals, y equals 50 minus 10x. If I put in the 0 right there, that means that that term cancels out, so y just simply equals 50. And that's our other intercept. So I've got a dot down here at 5, 0. I've got a dot up the side. Ooh, that is so fuzzy. I can't see it. Let me see. I believe it's up here. And then, of course, those two are connected together. So for our intercepts, I would write those down. 5, 0 is one of my intercepts, and the other one is 0, 50. Now, what do these mean? Well, let's go back and read the problem. I never did read the problem when we started out, and is the dilemma for some of you that you don't know how to do this one because you didn't read the problem. Jennifer started with $50 in her savings account. Each week she withdraws $10. The amount of money in her savings account after X weeks is represented by the function f of x, or y equals 50 minus 10x. Well, that makes sense. If she's got $50, she's taking out 10 per week. That graph basically shows how much money she's going to have over the weeks. So what does the intercept 5, 0 mean? Well, the first thing, the 5, is the number of weeks. So if we go across at 5 weeks, how much money does she have? Well, she has 0. So at 5 weeks, she, whoops, sorry about that. She has $0. She has no more money. After 5 weeks, she spent it all. So that's what that intercept means. The intercept 0, 50 basically means that at week 0, how much money does she have? She has $50. So it's pretty easy to say what the intercepts mean if you understand what an intercept is. Basically, at the zeros, it's going to mean one of your values is nothing. The other value is whatever the dot's on. In this case, the graph was labeled weeks and then the amount of money. So the one that you'll have on your test will be similar to this. You're going to have to read the problem and make sure you know what it's talking about. Okay, let's get these two. Let's find the slope. We're switching gears a little bit. Finding the slope you can find in your section 5.3 notes, I believe. When you're counting slope from a graph, you're going to have rise over run. So from this picture, I'm going to count my rise over the run. So from this bottom dot, I would count up and over to the other dot to figure out what the slope is. So if I'm down here at this dot at positive 1, I'm going to count up 1, 2, 3, 4, 5, 6, 7, 8 spots. I'm trying to get even with the other dot. So my rise for this problem is 8, and it's positive 8 because that's how many steps up I went. My run is going to be 1, 2. It took me two steps to get over to that other dot, and since I went to the right, that would be positive 2. Well, 8 divided by 2 equals 4. So that's your slope for this problem is positive 4. You can write it 4 over 1 if you want to, because technically our equation is rise over run. All right, number 12, same exact thing. I'm going to take this dot and I'm going to count up and over to the other one. So I would go up 1, 2, 2 steps. So that was positive 2 up. And then I'll count over 1, 2, 3, 4, 5, 6 steps to the right, so that would be positive also. 2 over 6 reduces to 1/3, and that's my slope for that problem. All right, I've got about a minute left on my timer, so I'm going to go ahead and stop the video on this one. If you'll please watch part number 2, that'll pick up with problem number 13.